Alright gang, here we go. This is for Chem 1, Unit 10, Part 1. We're talking about kinetic molecular theory. Going to review it real quick, and then we're also going to talk about pressure. So this whole unit is about gases, alright? All about these gases. Okay, so we've talked a little bit last unit about properties of gases, and now we're going to take it a step further and be able to predict their properties and be able to quantify. Remember, when we say quantify, that means we're actually going to put numbers with them. All right, so just to review some of the things we learned last unit about gases, we had the kinetic molecular theory, so that and in general, these are the main principles here. The particles in a gas are considered small hard spheres with insignificant volume, and this is when compared, all right, to the volume of their container, all right, whatever container they're in. All right, so they're these little small bit. You can almost picture like really tiny billiard balls, right? And they're kind of bouncing off the walls in there. They're really tiny, especially compared to the size of the container, right? Remember, the container is really big compared to the size of those molecules or atoms or whatever we might be talking about for these gases. The motion of the particles in a gas are in rapid, constant, and random motion, right? Okay, so they're bouncing off each other, right? They're running into each other, careening off each other, then careening off the sides of the container. You could imagine it's almost as if like you had just a big container of billiard balls, okay, and then and then you hit those billiard balls, right? And then they kind of scatter everywhere, but there's no friction. Okay, and so they're bouncing off each other or the walls of the container. Okay, and which would be the bumpers around the outside, so on and so forth. And then we also make two important assumptions about these collisions that they have. Number one, there's no attractive or elastic forces that exist between the particles. So we just assume they're moving so fast that the intermolecular forces don't matter. Okay, and then number two, we assume that all these collisions between the gas particles are elastic. There's no kinetic energy that's lost between them. How the total kinetic energy before and after their collisions is the same. Okay. A couple other properties of gases we need to remind ourselves of is they're easily compressible. Remember, this means that we can take our gases and contain them into a smaller space. So because they always take up the space that they're in, they're always going to have the volume of their container. And then if we can reduce the space by increasing or decreasing that volume. And we can do that because there's massive amounts of empty space between these gas particles. All right. Number two, gases expand to take the shape of their container. Okay, they're always going to try to be as spread out as possible. It just depends on how big of a container you put them. And then number three, if we add gas to a container, the pressure goes up. Okay, and that makes sense, right? If we remember, pressure is caused by the collisions of these particles on the outside of your container. Okay, and so they're careening into the walls of this container, and if they hit the walls of the container, they're going to be adding a force to the walls of the container, and that's what pressure is. Pressure is force over a given area, and so if we increase the force over a given area, then the pressure goes up. So if we add more particles, that means we're going to increase the number of collisions, and thereby the number of collisions against the walls of the container, and then therefore the pressure would go up, right? Now, we need to be able to work with pressure, and so far what we've done is we've been able to talk qualitatively about pressure and be able to say, well, if we do this, this will happen to the pressure. If we go up a mountain, the pressure goes down because there's less particles, etc., etc. Now we need to take these pressure and be able to quantify it, okay? And so the first thing we need to talk about is units, okay? How do we quantify these pressures, okay? These are the pressure units that you should be familiar with, okay? Number one is millimeters of mercury, okay, and this comes from, remember when we talked about pressure, we talked about if you had like a container of mercury here and then a test tube, a barometer, right? This is when we talked about, how to measure pressure. We talked about barometers, right? And so this pressure is pushing down from the atmosphere, is pushing down on this mercury. Because it's pushing down and there's no air in here, remember this was an evacuated tube, the mercury gets pushed up inside of this container, okay? And then we could measure how high the mercury goes, right? And then so this distance here, it would be measured in millimeters, and because it's mercury, it would be millimeters of mercury. Okay, I also affectionately call it squiggle squiggle Hg, all right, because my M's tend to run together when I write it. So anyway, so we've got millimeters of mercury here, All right, and so it goes up, and so on and so forth. So that's really where we get this unit for pressure is millimeters of mercury. All right, then the next one here is standard atmospheres. Okay, and we use this one a lot because it's based off of the atmosphere of the Earth. Okay, 1 atmosphere is about the pressure at sea level. Okay. All right, and chemists, we use this unit a lot because this is the standard. Okay, or we work in laboratories that have pressure very much like the Earth's, and so therefore we use 1 atmosphere. The next one here is torr, and this is named after a chemist or a physicist, I think, named Torricelli, and he was a Italian guy. Now the funny thing about him, it's capitalized here because I couldn't get it to uncapitalize when I made the PowerPoint, but it should be a lowercase t. Okay, and it's named after this guy, but most people don't know that. It is just kind of like this forgotten physicist that somebody that was like very important, but now he's just kind of like lost to time. People just say it's a torr, and then the torr, 1 torr is equal to 1 millimeters of mercury. So essentially, they're like, millimeters of mercury is too hard to say, so we're going to call it a torr. Okay, but for millimeters of mercury is still kind of is still sticking around. So he's just kind of like this lost unit that somebody really tried to help him out, but it's not quite working out anyway. And then we also have pounds per square inch. Okay, this is kind of what we use. It's also known affectionately as PSI. Okay, so in America, when we fill up our tires, we say we're going to like 30 psi or 35 psi or something like that. And so we're talking about how many pounds per square inch. So for every square inch, how many pounds do we have, et cetera, et cetera. And then the last one that's not on here is that we've talked about before. Oh, it is right here. It's called the Pascal. Okay, right here. This is the SI unit of pressure. Okay, the Pascal, but it's really, really small, like absurdly small. Okay, so small that if we were going to measure the pascals of the room pressure, just atmospheric pressure at sea level, it would be 101,325. So it makes your pressure units really big. So for the most part, we don't ever use pascals by themselves. We use kPa, which could be kilopascals. And remember from when we learned about the metric system, adding a k in front means you divide by 1,000. All right, so we use kPa's more often than pascals. All right, so then we get our standard air pressure. So this right here is very important. This is how you're going to convert between all these different pressures, because we need to be able to take these pressures and be able to convert them from one unit to the next. Okay, so 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 101.3 kPa, which is equal to 14.7 pounds per square inch. So essentially, this is if you were at sea level, this is the amount that you have. And so because they're all equal to each other, we can use this as our ratios in our dimensional analysis. So let's do a couple practices here. All right. It says how many kPa are there in 720 millimeters of mercury? All right, so we have 720 point millimeters, squiggle, squiggle, Hg. So this is what we're starting with, and this will look really familiar, right? We draw our little parentheses here. We start with the unit we're starting from needs to cancel, so it's going to go on the bottom. So we put squiggle, squiggle, Hg in the bottom. What are we going to? Well, we're going to kPa, so we'll put kPa up here. All right, now we just go to our thing here, and we find our two guys. We have 760 for millimeters of mercury, so we'll throw 760 in down here. All right, and then we have 101.3 for our kPa. So we go 101.3 for our kPa. All right. Easy enough. So now we just take our calculator. We say 720 times 101.3 divided by 760. And we get, so that guy out there has 3 sig figs, so we want 3 sig figs. So I got 95.968, so the 6 makes the 9 round up, so it'd be 96.0. And the units here, millimeters of mercury, cancel here and here, so we'd be left with kPa. Easy peasy, all right? This says how many torrs are there in 2.3 atmospheres? Well, same idea. We've got 2.3 atmospheres. Draw our little dimensional analysis parentheses. Atmosphere is going to go on the bottom because that's where we're coming from, and we need it to cancel. And torrs are going to go on the top. All right, so we put torr up there. All right, we go and we find atmospheres and torrs. So atmospheres right here, torrs are right here. So it's 1 on the bottom, 760 on the top. All right, well, 1, 760. All right, and Bob's your uncle. So you'd say 2.3 times 760 divided by 1. All right, 2.3 has 2 sig figs, so we'd be 1700 torr. or 1.7 times 10 to the third. And that's it for part 1, guys. You made it. Oh, I lied. There's one more bit. So every once in a while, we have this idea, or this, you'll see this phrase come up, STP, and we've seen it before when we learned about mole conversions, right? In stoichiometry, we learned about STP conditions. But just to remind you, standard STP stands for standard temperature and pressure. Okay, and so this is defined at these values: 0 degrees Celsius or 273 Kelvin. Remember, these two are synonymous. Okay, they mean those are both temperature systems, or both temperature units. These would be equal to each other. They're both at the freezing point of water. And then the pressure would be atmospheric pressure, so 101.3 kPa, or 1 atmosphere. All right, so these are, so when you see this phrase, you'll see this pop up in a lot of your practice problems that say something like at STP, and so you'll remember that this means the temperature is 0 Celsius, 273 Kelvin, and then the pressure would be 101.3 kPa, or 1 atmosphere. All right, and so that's truly it for part 1. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.